All right, so I think we have a great session here for the next hour and a half or so. It's the Storm Surge and Coastal Impact session. My name is Cody Fritz, and I'm the Storm Surge Unit Lead at the National Hurricane Center, and I'm accompanied by Saeed from the National Ocean Service. He is online, so for anybody that has questions, they can certainly ask them there, and he will do his best to answer them, if not in the room as well. I'm not going to belabor this too much longer, so let's just go ahead and get started here with the talks. Our first presenter here is Yuping Lee from Florida International University. And I'll let you take it away, Yuping. He is online.
Thank you, Cody. Can you hear me?
Yes.
Okay, I will start. Thank you, everyone. My presentation today is about anisotropic subgrid correction for storm surge model. I should thank Mr. Horan Sun from University of Notre Dame. He did most of the coding part to employ the subgrid correction into coastal extreme storm tide model. Next. Grid-based numerical storm surge model use the two-dimensional shallow water equation. Generally, final mesh enhance the accuracy of flooding prediction because they take more information into consideration. Nowadays, high resolution data has become more and more available. However, it's been very expensive to run the simulation in this high resolution data set, like 10 meter, 30 meter. This brings us a gap between simulation resolution and the best available represent of the coastal geometry. Next. We believe that the subgrid correction could be a good solution to bridge the gap between the high resolution data and the coarse grid simulation. Subgrid correction technology introduced an average shallow water equation and the closure term to effectively represent high resolution information while maintaining a coarse grid level and the large time step. Generally, the workflow is using the high resolution data to generate an average variable to forcing coarse grid simulation. In this way, we can take the high resolution information into consideration while still maintain the coarse grid level computational cost. Next. Developing subgrid technology into an established model could be challenged, but it's still worthwhile. Consider that this model, like Slush or SEST, they have been already satisfied computational efficiency and the numerical stability. This table showing that the comparison between Slush and the SEST model. One unique feature of SEST is that SEST can directly use Slush grid, which makes two models to cross-check the simulation result in the same domain. In this study, we are exploring the implementation of the subgrid correction into the storm surge model. SEST. SEST is a coastal extreme storm tide model developed at International Hurricane Research Center of Florida International University. It used the semi-implicit finite difference scheme in the ArcC grid and several widely accepted numerical scheme. Previously, study has shown good numerical stability and accuracy. Next. The starting point of this research is to derive the set of average shallow water equation and the corresponding subgrid correction in Cartesian coordinate. By applying the coordinate transformation, we have the average shallow water equation and the subgrid correction in orthogonal curvilinear coordinate. The current subgrid model use correction for water height, bottom friction, and wet friction. We wanted to highlight that separate from the corresponding nonlinear solver and the correction, that the description follows the previous scheme and no further modification are needed. So make the subgrid correction easy to imply in the established model. Next. Several numerical schemes had been implied in this study by subgrid model to improve the accuracy and the numerical stability. Numerical scheme used here include the theta scheme for the mass equation and the bottom friction and the surface elevation term. A conservative extension of the advection term is used here. Three order third order Adam best force scheme is also applied to the Coriolis force and the coordinated transform. Next. Several cases of the wetting and the drying had been tested in the present study. In the first case, oscillatory flow with moving shoreline driven by initial surface elevation in a bowl shape of the basin is considered. The red line is the bathymetry and the blue line is the initial surface elevation. This case is a challenge. Consider the error introduced by the shoreline movement will contaminate the solution in the whole domain. A parabolic cylinder grid is used here to as the computational mesh. To correct the computational grid variable, a subgrid mesh with a mesh resolution is around 1.6 kilometer is used. In this case, the subgrid is 20 by 20 for each primary cell. The simulation results are varied with the analytical solution. Next. Here, several of the results are highlighted. In the coast grid, the surface elevation at the time equal to 6 cycle is selected to present. As shown here, the original simulation of SEST is contaminated by misrepresenting the wetting and the drying front. A smoother result is generated by the subgrid simulation, and it agrees better with the analytical solution in the right panel. Next. The time series of the surface elevation at 3 stations along the wetting drying area is shown in this slide. The black solid line is the analytical solution, and the red dashed line is the original SEST. The blue line is the subgrid result. It's clearly that the subgrid represented the analytical solution much better than the red line, the original original SEST. Next. The second case considered here is the storm surge induced by Hurricane Florence. In 2018, we did several grids to test different resolution results. In this study, the original SEST grid resolution is about 40 meters. Subgrid mesh with the resolution can be reached to around 6 meters. In this case, the simulation are validated with the observed data. All the water level sensors are considered. Overall, totally is about 88 stations by NOAA or USGS are used in Figure 1. Figure 2 showing the bathymetry of the grid. The present study test, next. The present study tests 3 wind products, HWRF, generalized asymmetry Holland model, and the sludge wind field model. The coast grid simulation error metrics for different wind data is shown here. 3 error metrics are used to compare: root mean error square, coefficient of determination, and the best fit slope. Hydraulic connective and the represent of the coastal geometry was improved significantly in the subgrid, in which only 1 observed location was not wetting during the storm surge simulation in the black box shown. But for the original grid, it's left 21, 16, and 19 station stay dry for different wind-driven force. So subgrid SEST outperformance SEST across almost every statistic analysis. The scatter plot also showing that the subgrid has better simulation results than the original method. The simulation time for the subgrid increased only 50% to 8% of the original grid. The original grid is take about 3 hours to finish 4D simulation, but the subgrid it take about 5 hours. Next. Furthermore, a time series of surface elevation at open water station and the inland station is shown here. The black line is the observation. The solid color line are the subgrid simulation, and the dashed color line are the conventional simulation result. The original SEST grid suffers from represent the correct bathymetry, like in the station S1. It stays dry in the beginning of the simulation, but the subgrade simulation result, the solid line in all open water stations agree well with the observation. Next. The third case is the Hurricane Ian 2022 simulation. Since SEST can directly simulate the surge on slush grid, this time we use the South Florida slush basin to perform the simulation. Next. The Fort Myers region is selected to demonstrate the subgrade feature. The right panel showing that the topography and the bathymetry comparison between the original slush and the subgrade. In this region, original slush grade can represent well in the Caloosahatchee River, but not the small tributary in the bottom, the Bailey Creek. Use 32 by 32 subgrade. Bailey Creek can be well present. The original slush grade resolution around this region is about 350 meters. With the subgrade, it can reach to 10 meter by 10 meter. Next. Around the NOAA tidal station, Naples station, the subgrade can also well represent the small tributary and complete the bathymetry near the coastal area. The detailed coastal infrastructure and the complex terrain is well resolved using the subgrade compared with the original grade. Next. It takes about 1.4 hours to finish the 3-day simulation use the original grade, and it takes about 3 hours for the 32 by 32 subgrade computation. It's double time. The time series comparison at the NOAA tidal gauge indicates that both SEST and the subgrade can reproduce the surge well in all 9 NOAA tidal stations. The scalar plot of the high water mark comparison showing that the original SEST grade can only catch about 270 points, but the subgrade can catch about 300 points. It's 10% more. Next. The inundation depth comparison at Fort Myers indicated the original SEST grade is only flat 2 or 3 computational cell along the Caloosahatchee River and the Bailey Creek. But the subgrade produce more flooding extended area along the river, especially that the surge can further propagate to the upstream of the Bailey Creek, which cannot be resolved in the original grade. Next. The inundation depth comparison at Naples indicates that the original SEST flood most coastal area, but the subgrade produce less flooding extended area along the coastal zone. Some of the relatively high land stay dry during the hurricane period. So, next. In summary, within each primary grade cell, the subgrade add local detail capture the fine scale feature such like the complete coastal line, narrow channel, and the local topographic change. Instead of calculated detailed dynamic everywhere, the model only performs high resolution computation within the subgrade cells where they are most needed, such like the coastal infrastructure or complex terrains. Subgrade correction is especially beneficial in the storm surge modeling, where high resolution detail is only essential near the shoreline, inland, or the natural hazard area. We can find the grade around that area. Thanks. That's all. Any questions?
So we'll leave questions for the end. So Yuping, hopefully you can stick around until that point forward. Sorry. All right. So our next speaker should be Ben Trabing, who works with us at the National Hurricane Center and UCAR. And he should be presenting on some new modeling work within the Pacific region. So.
All right. Thanks, Cody. Can everyone hear me?
Yes, we can definitely hear you. Just give me 1 second because we've lost visual. Okay. All right. So you're going to control the slides. You're going to do it. Okay, then go ahead when you're ready.
All right. Well, yeah, you can kind of go ahead to the next slide. So yeah, I'm going to be kind of giving an update on kind of P-Surge operations and looking at kind of what the storm surge unit's been up to. My name is Ben Trabing, and a lot of this work has been done by not just myself, but Andrew Penny, as well as everyone else from the storm surge unit, and MDL has also contributed to this. So just to kind of give first off kind of a recap of 2024, it's been a pretty busy season. We've had 8 storms that have required the issuance of storm surge forecasts, going from the early storms from Alberta, Peril, and Debbie, Ernesto actually having forecasts for storm surge, and that was a case for Puerto Rico. Rafael actually even had some forecasts, and then Milton and Helene kind of the big impacts there. So I'd love to be able to show kind of verification of how well the forecasts actually looked and kind of verification of P-Surge. But unfortunately, with the number of storms, the number of observations that we have to quality control and analyze, that's just not quite ready yet. So hopefully we'll be able to talk on that a little bit later. All right, so go into the next slide. Just kind of want to give you some, first off, some background of how we actually forecast storm surge from the storm surge unit perspective. We actually use the probabilistic storm surge model called P-Surge. P-Surge is an ensemble of sea, lake, and overland surge from hurricane model runs, which is called SLOSH. So SLOSH being that hydrodynamical model that's really being forced by the different wind perturbations that we're actually using. And so we're using this based on the NHC forecast, and we're using historical errors for kind of accounting for that uncertainty in the cross-track direction, the along-track direction, and we have 3 different members that actually go in for kind of perturbing that intensity of the storm as well. And then the last thing we actually incorporate is uncertainty with the storm size. Now, since NHC doesn't actually forecast the radius of maximum wind, we get that from a multivariate linear regression technique that's kind of using the official forecasts and the 34, 50, and 64 knot wind radii. We then get the errors from that kind of regression model. We can then use and kind of plug into P-Surge to actually incorporate that uncertainty. And of course, we do this because we know that storm surge is a very localized phenomenon. Small changes in the track of the storm can impact the storm surge substantially and significantly change what actually happens. So if we go to the next slide, the SLOSH model, the hydrodynamical model, one of the more recent things that we've been able to do is actually couple it to a wave model to actually incorporate wave setup. Now, this is really important when we're actually looking towards kind of expanding P-Surge to areas and island environments where we don't have this gentle continental shelf, such as along the Gulf Coast, and wave kind of driven impacts to that total water level rise are going to be a little bit higher. So if you kind of go into the next, you click once, what we're actually really focusing on now is Guam, Hawaii, and American Samoa. So these basins have been developed actually starting going back into 2014, but these have never been kind of introduced into P-Surge. So that's really our main thing that we're actually focusing on now is actually expanding P-Surge to different regions. Really what we're focusing on is Hawaii at this point. So if we go to the next slide, historically P-Surge has only been run out in the Atlantic. And so we've only had to use the National Hurricane Center's forecasts, and the National Hurricane Center's forecasts their air distribution. And so when we're going out to Hawaii, we actually have to use CPHC's forecasts and CPHC's forecast errors. This became a little bit more of a problem when we look at the sample size. We love to use that 5-year running mean for the sample size of the errors. And it's kind of hard to do in the Central Pacific where we don't have a lot of storms. And there's a lot of year variability, especially with ENSO. So we actually had to redo a little bit of this and kind of work on kind of blending National Hurricane Center forecasts in the East Pacific with Central Pacific forecasts from the Central Pacific Hurricane Center. And so we did a little bit of this blending, creating a normalization factor, kind of incorporating them. And that was kind of a lot of the front end work and kind of making sure that our air distributions and the forecasts that we're actually going to be putting into P-Surge are the best that we actually can. So we actually able to use the RMW errors also from the regression model in the Atlantic. We tested some different configurations there, but overall found that the method that Andy developed for the Atlantic actually did better in the Central Pacific and East Pacific compared to in the Atlantic. All right, so if we go to the next slide, we actually got a really great test case this year with Hurricane Hone. So if we weren't kind of focused in on Hurricane Hone or what the impacts from the Central Pacific were, we actually got 4 really nice synthetic aperture radar overpasses from our SAR, kind of showing the evolution of Hurricane Hone as it approached the island, going from this kind of weaker tropical storm to kind of an asymmetric, kind of more consolidated tropical system to a symmetric hurricane really close just south of the Big Island before opening up again out into more of an asymmetric tropical storm again. But this was a great test case. We were actually able to run a P-Surge in the Pacific kind of in parallel this year to actually do this for any test cases. And so if we go to the next slide, we were actually able to kind of validate how well the ensemble did as well as the actual exceedance values. And so this is actually just kind of the track evolution in terms of one of the forecasts on the top. The bottom left is actually the intensity forecasts, the 3 different members, as well as the black being what actually was observed. And then the bottom right here is actually the RMW, 3 different members. And we're really happy with how the ensemble overall looked. The track was pretty much always within that ensemble, looking at all the different forecasts. The intensity was a little bit more mixed. It was kind of near that upper bound for what we would expect based on the intensity errors from CPHC, kind of hovering near that 85th percentile. And the RMW was pretty much always kind of constrained within there, which was also good to see. There were pretty much really good forecasts all the way across the board. The only really one time where it actually didn't do quite a great job is actually just 12 hours prior to kind of the closest approach to the Big Island, where Hone actually kind of rapid intensified by 20 knots in 12 hours. And so that really wasn't well forecast. And because of that, it also wasn't well communicated within the P-Surge ensemble as well. But if we go to the next slide, we can see how well the 10% exceedance probability has actually looked. And so this is at different lead times, so 60 hours prior to the closest approach, 48 hours, and then 12 hours. These are the 10% exceedance water levels in terms of feet above mean sea level. And overall, what we see here is that all of these kind of plots are blue. We never really saw any probabilities exceeding that 3 feet threshold. And they were also pretty consistent with time. There wasn't a whole lot of cycle to cycle variability, and overall these were pretty stable. So we're really happy with this. If we go to the next slide, one of the issues though with trying to actually verify how well P-Surge actually ran for any of these Hawaii cases, or looking even for Guam and American Samoa as well, was actually just trying to find cases that we could actually verify the model with. So this is actually taking a look at a whole bunch of different storms that we could find with at least some observations at one of those 3 different island basins. And really the only storm that we actually had, for instance, for Hawaii, that actually had water levels that were actually observed at one of these NOAA tide stations above 3 feet was Hurricane Iniki back in 1992. And that was the last major hurricane to actually impact the Central Pacific and impact, Central Pacific, to actually impact Hawaii and make landfall there. And for Guam, there's a couple of other cases. So Mawar from 2023 was on here, 2 feet of surge. But we're going to be mostly focused on Guam and American Samoa, kind of the later update. But if we go to the next slide, I just kind of wanted to show, if you don't remember what Hurricane Iniki looked like, it made landfall in Kauai as a major hurricane. It is the last major hurricane to make landfall. And of course, knock on wood, that this doesn't happen. And we don't actually have to use P-Surge out here for a while. But this is really the main test case that we've actually been working on. And overall, just doing some verification, it does overall a pretty good job at actually capturing those water level rises, and it compares really well with the tide gauge, particularly looking at how the evolution evolved with the tides. And if we go to the next slide, so for this next year, when we actually incorporate P-Surge into the Pacific and actually run it for Hawaiian operations, just kind of want to give you a sense of the workflow for this. So CPHC's forecasts, they'll be synced up through the ETCF at NHC. And so we'll get that information at the National Hurricane Center. The storm surge will actually be the ones setting the initial water levels and actually kicking off P-Surge. So that will all be kind of initialized from the storm surge unit. The output will then get disseminated to CPHC through their AWIPs, and we'll do some additional coordination there. And then the storm surge unit will be the one kind of coordinating and creating any graphical products related to the storm surge, such as the inundation graphics, the peak water graphics. And all of that's really going to still be coming from the storm surge unit. Now, if we go to the next slide, I wanted to kind of shift gears and talk a little bit more about kind of what we're actually now starting to look at in terms of development and kind of improvements to the model. And we know that storm structure is really something that we really need to kind of focus in on and improve. And so this is kind of a comparison between a couple of other synthetic aperture radar overpasses from Hurricane Idalia in 2023 versus Hurricane Helene. And you can see the substantial size difference here, right? Size really does matter, particularly for water level changes and the storm surge. And that's one of the reasons why Hurricane Helene had a much bigger impact compared to Hurricane Idalia in the Big Bend region. We go to the next slide, how this actually translates to the waters, and looking at, for instance, the kind of the hindcast for Hurricane Idalia. On the left is actually the wind field using the kind of the best track RMW and the best track intensity. And you can see how that wind field looks. It's a relatively small storm, kind of matches up what we saw with the synthetic aperture radar overpass on the last slide. But then when we look at, for instance, kind of in this Tampa Bay region and East Bay, what we find is that the wind field is a little bit too small. It doesn't really encapsulate what actually happened out in East Bay, where the water level observations don't really match up with what was actually forecast from slosh based on the size of the storm here. So then what we have to do is adjust the storm size by kind of increasing that RMW. And what we do is based on kind of looking at the bigger storm structure, we can actually better match up the observations in East Bay and better communicate what actually happened there. Now, this actually does a really poor job at, of course, at actually getting what actual impacts there were near the landfall point. But in terms of actually getting the outer core region, slosh was a little bit underdone in terms of the winds out in the outer core. So if we go to the next slide, this is a lot of work done by kind of Andy Penny and looking at a retrospective sample size and kind of comparing P-surge and the slosh wind fields with the WTCM and, of course, the best track. And so this is just kind of looking at the distribution of the radius of maximum wind and intensities that we have within the P-surge retrospective forecast data set. There's 182 total storms here, pretty good distribution. And then if we go to the next slide, we can see how well these actually compare. And so on the left here, we have the radius of 64 knot winds, 50, 34, and then on the right is the radius of maximum wind. And these are the different mean values for the best track in black, the slosh wind field in red, and then the WTCM in blue. Just to kind of focus in on the radius of 34 knot winds to start, we see that slosh really underdoes the radius of 34 knot winds, whereas the best track and the WTCM are more constrained and more similar to each other. We would hope to get slosh to better analyze the radius of 34 knot winds kind of at those values. But if we look at, for instance, the radius of maximum wind, slosh is more constrained to the radius of maximum wind, is better matching what's actually occurring in the best track compared to the WTCM, which actually has a bit of a low bias in terms of the radius of maximum wind, about 10 to 50 nautical miles. So both have their advantages here, and we're kind of an active project to try and actually improve both of these together and actually incorporate them and couple them with slosh to actually drive the wave models and the hydrodynamical models. So if we go to the next slide, just kind of summarize, 2024 has been a pretty active year with 8 hurricanes and tropical storms that we've actually had to provide forecasts for. Verification of kind of all of those forecasts is still upcoming once we get all that data and we can quality control it and kind of go through it. We were able to run P-surge this year in parallel, and Hurricane Hone provided us a really nice test case. We were able to disseminate all that information to CPHD in real time. And for 2025, that's going to become operational, where we're actually going to be providing forecasts for storm surge through the P-surge model out in this region. Other updates that we've actually improved on is kind of calculating those P-surge air statistics and updated those for the Atlantic. So that hasn't been done since prior to 2020. So we've been able to update those. And then we've also been working on kind of various other smaller bug fixes and updates to the model itself. If we go to the next slide, just kind of talk about kind of what's up and coming. So I mentioned Guam and American Samoa. We're hoping that that's going to be operational in 2026, and we're going to be running that kind of in parallel this year. There's still some work that we need to be done in terms of developing the ConOps for that. Overall, we have the errors and overall P-surge is configured to run for those, but we still have to do some additional tests and modifications there. Other updates that we're working on is kind of testing and examining higher resolution and larger slosh basins. So if you look at kind of the number of slosh basins on the top right here, there's a lot of them. They're kind of small, a little bit coarser. And so we're kind of trying to move to these kind of super basins, which are in the bottom right, or much larger basins, but higher resolution. This is going to help with kind of the connectivity and helping with the overlaps there, as well as kind of better analyzing the overall storm surge coming from those through the higher resolution. We're also working on kind of improving that wind forcing within P-surge. I mentioned that we're looking at the WTCM, comparing that with slosh. We're trying to get the WTCM coupled to slosh to analyze that. We're also working with another parametric wave model or wind model called PAM, and trying to figure out which one of these is going to be the best and which one we're actually going to be able to provide us the best forecast moving forward. And then, of course, we're always working on improvements and other bug fixes to P-Surge, but there's no surprise there. So that should be it. So if you go to the next slide, if you have any questions, if we have time, or I guess we'll do that later on.
Okay. All right, thanks, Ben. Please stay on if you can until the end of the session. So we'll kind of get this going again. So our next speaker is Sarush Mani from NOS OCS. And so you are in person, which is great. So take it away when you are ready.
Okay, thank you. Should I start? So, hello everyone. This is Sarush Mani. I'll just go ahead and whenever you're ready. From Office of Coast Survey. So today I'm going to talk about a collaboration effort that we have with National Hurricane Center Storm Surge Unit. And this is for, basically it's an exploratory project for improving the existing P-Surge with a high resolution unstructured grid model. So first, let me talk a little bit about our team at NOS. So Office of Coast Survey, which is a part of NOS, is responsible for safe navigation and coastal resilience. And as a part of that, our team, the Storm Surge Modeling team, is operating or basically running a couple of operational models, such as STOF's 2D Global, STOF 3D Atlantic, and soon STOF 3D Pacific. These models are important in our portfolio, and they support marine chart navigation, charts for marine navigation, as well as they are upstream to models such as National Water Model and the nearshore wave prediction systems. It also actually, I forgot the last one, but basically, the other side of the team is the research and development team, which I'm a part of, and it is mainly supports the research type of the stuff that we do, the exploratory project with lower readiness levels. That includes STOF 3D Alaska, mesh development, as well as the UFS Coastal. Also, the things that I didn't mention, I didn't write here. One is the using GEFs and HAFS for ensembles for forcing the schism, basically the model behind STOF's models. By the way, the STOF's model is forced with GFS right now, so probably next step is basically the GEFs. But what I'm going to talk about today is mainly the collaboration we have with the NHC, which is the first project I highlighted there. Slide, please. Previous one. So, thanks. This collaboration, as I said, is mainly focused on exploring using the high resolution unstructured grid model, specifically Schism, to see how it augments and complements the current P-Surge model, specifically for short lead times. So as a part of that, basically, as a part of this project, we defined some tasks that we're currently working on. As Ben mentioned, one part is evaluating the vortex models and wind fields, which is being done by the NHC, and also deterministic evaluation of schism and slosh is something that NHC is looking into. On our side, we're developing a framework, which I'll get into in the next slide, and why we really need that. And also, developing and evaluating this probabilistic framework, and we're hoping to be able to set up a schism run, deterministic schism run for next season with a single official track to see how that deterministic run results are and skill is compared to the again probably a single track slosh or like in general with the probabilistic results from P-Surge. Next slide, please. So again, talking about the framework, that main reason we need to have this framework is because we're going to have a high resolution model, so we might not be able to really have as many ensemble members in a given time. So we went with a traditional machine learning approach where we were using KLPC for dimensional reduction and basically polynomial chaos theory to fill in the blanks. So we have a smaller ensemble size, but we're filling in the blanks using this machine learning approach. And so this is built off of existing work by my colleagues at NOS and Argonne National Lab. And we're kind of, in the current work, we're kind of modifying it a little bit to improve the results. But basically, we can get exceedance levels, the sensitivity results, and compare it with the pre-search using the ROC curves. Currently, the probabilistic model results of this framework is only based on the max elevation, but we're looking into also taking care of the time-based results. Next slide. So the framework is very similar to what P-Search does. So we are basically perturbing 4 variables across track, along track, storm intensity and storm size. And the last 2 as defined by Vmax and RMW. In the new approach, we call it V2, we're using the RMW filling method, or basically regression method proposed by NHC last year. And also, in addition to that, next slide, please. We are looking into using GAM, again, from the model that Ben mentioned, the PAM, which is a suite which has GAM, Holland, and a couple of different models. So we're using GAM now to address the symmetry. So in order to be able to really use PAM's GAM model, we also need to perturb the ISO tax. Now the problem is the ISO tax, we only perturb the RMW, and to be able to keep the uncertainty the same as before, to be able to compare it with the previous work, we really need to come up with a scheme to adjust the ISO tax. And what we're doing right now is we are getting the GAM parameters, because B, G, and Phi, from the track using an iterative approach. And then we perturb the track, perturb the RMW, not the ISO tax. And then again, through another iterative approach, we get back the ISO tax from the perturbed RMW. And so with these improvements, we're looking into the results. This is currently in progress, and we're really looking into the results to see how much improvements we get. Next slide, please. The other part of the work we're doing is addressing the time-based results. So the basically most naive approach is to use the same framework, but do it instead of using it on the max. We just kind of go step by step, and for each time step we'll look at that. But that kind of in terms of timing, it will be very bad because it linearly increases with the number of time steps that we have. So we're next slide, please. So we're looking into using deep learning, specifically LSTM, to see how it handles the timing with multi-time analysis of this, multi-time step probabilistic analysis of this ensemble. And next slide, please. And so this is a very preliminary results from that time series analysis. So as you can see, the progression of the exceedance levels based on time for a fixed ensemble, for an ensemble with a fixed lead time. Next slide, please. And so everything that I talked about is really in progress, and we don't have any final results. Hopefully we'll have better results to present at AGU next month. I don't know why the numbers are messed up like that, but so the next steps are testing and validating with more storms. Right now we're looking at 3 storms just to begin with, and then we'll expand it to more storms to really compare it with P-Surge. And also we need to look at different combination of things, such as using GAM model or comparing GAM model and Holland model with different RMW schemes, or using GAM or comparing GAM models with the new RMW versus the old RMW. At some point, we're going to explore the including wave effects. Probably this is going to be done through the UFS coastal when it's ready. And definitely we need to improve the time series in terms of runtime. And as I mentioned, we're going to present the results later. Next month in AGU. Well, thanks.
Thanks, Sarush. So the Ocean Service, National Ocean Service's work is really instrumental in helping us build the next generation storm surge model, one that we'll implement in the coming years. So we really appreciate their collaboration with this. So our next speaker is, I believe, Joseph Zhang, and he is online. Is that correct?
Yeah, I'm here.
Okay, we can hear you. So as soon as they have it ready, I'll let you. You're good? Too many windows, right?
It is.
All right, Joseph, I think we're ready. So Joseph Zhang from the Virginia Institute of Marine Science. Take it away.
Thank you. Good morning, everybody. So I will give a talk on our collaborative work with LOA organizations. Sarush gave a very nice introduction to the modeling framework we are developing, specifically related to the auto mesh generation. I'll circle back to the mesh generations in a couple of slides, but I'm Joseph Zhang from, I'm a professor from Virginia Institute of Marine Science. So this is a large collaborative work. Sorry, Sarush, I missed your name here. But we actually had a recent paper, so Sarush is the co-author. So next slide, please. So this is an overview of my talk. I will give you some compelling reason, I think, why 3D model is really necessary for total water levels. I will discuss briefly about the choice of vertical datum, and I will dive right into the Stuff 3D Atlantic system we are developing with LOA, and the specifically how we couple with the hydrology legend water model, and also I will briefly mention the automatic mesh generations, especially for those challenging watershed rivers. And I will give you some updates on the recent development on the hydrological regimes, and conclude my talk with summary. So next slide, please. So yeah, so most of the storm surge and inland flooding models are built on 2D models, right? So that's a given. But we know that observed total water level is really a combination of many, many factors. You have storm surge, you have river flooding, you have heavy precipitation, you have wave effects, and you even have groundwater effects. So some type of model coupling is probably needed, so that's a consensus. But for obvious reasons, a simple approach is preferred. So that's exactly what we proposed. So we're trying to simplify the coupling process as much as possible. But more importantly, we really need to account for the important 3D effects. So that's something 2D models are missing, because they do not account for those effects, and as a result, they need a bias correction. But the bias correction can only work for hindcast, where you have the observation data, or for very short-term forecast. But I will show you that the 3D models really been demonstrated well now with multiple publications we produced over the past 5 years. And those publications really demonstrate the power of 3D models, in accurately capturing the total water levels. So obviously, 3D models are more expensive. That's why fewer groups are using 3D models. So our job is really to make a 3D model as efficient as possible. So that it becomes more affordable, assuming that you have adequate resource, HPC resource, or GPUs, right? So we did lots of work there. And the another thing I want to mention is that with 3D model, you really open up exciting windows opportunities. right? So for example, for the atmospheric side, the air-sea coupling, especially in the nearshore region where the upwelling can play a role in the intensity of the storm or track of the storm, So Greg Soroka did this study in his PhD thesis. He published a couple of papers on that, So this kind of feedback loops, you really need help from the ocean model, and you need a 3D ocean model for that, in order to capture those kind of baroclinic processes. And of course, 3D model also comes with lots of co-benefits. You can use it produces a lot more output, and you can use those for other purposes such as navigation support, etc. Next slide, please. So, in terms of total water level prediction, one very important consideration is to have a very accurate vertical datum, right? So the water level is always referred to a specific datum. So one popular choice is NAVD 88, and we know by now it's not the ideal choice because it was based on the leveling at a single point in Quebec, Canada, and tied to a network of leveling benchmarks, and those benchmarks are not well maintained. As a result, you can have biases across the continent meter or even more. Next. So for large scale modeling, continental scale modeling, ocean basin scale modeling, geoid is generally preferred. So geoid is basically equal potential surfaces. It's hypothetical surface for the water level under the equilibrium conditions, right? So the gravity force is everywhere perpendicular to this surface, and it can be created, can be simulated using the satellite gravity data with a very precise measurement of surface shape and the gravitational field. So in this study, we used the XGeoid 20B, which is an experimental geoid being developed by NOAA, but we are moving towards the final geoid 22. So this is ongoing work. To cut the long story short, this really help us, to get a good handle on the total water levels. And the added benefit is that, lots of satellite-derived sea surface high data like ADT, right? So they are referred to the geoid. So as a result, we can actually use this as the long tidal component of the elevation to initialize and drive the model. So this is another added benefit of using geoid. Next slide. Yeah. So we've been working with NOAA groups to develop this STOF 3D forecasting system so the STOF 3D was originally designed to really to accurately predict the total water level at the continental scale, right? So this figure in the middle shows the current domain coverage for the STOF 3D. So the underlying engine is a schism. It's a 3D model, but it's not traditional 3D model in the sense that it really allows this kind of so-called polymorphism, right? So plots on the right shows you the vertical structure of the grid, right? So you can have as many layers in the deep ocean as you want in order to actually resolve those large scale processes. But when you go to shallow regions, near shore, go to the watershed, you can use this very efficient 2D depth average mode, right? So you can even go to the quasi 1D mode. So as a result, it greatly enhances the model efficiency because you no longer need to use same number of layers everywhere. And in addition, we also allow this kind of very high, flexible horizontal unstructured grid. You can use triangular, you can use quads, you can blend them. So this leads to great efficiency. So this system has been fully operational since January 2023, and right now every day we produce one forecast with 1 day nowcast plus 4 day forecast. So the turnaround time is about 1 day. Okay, I mean 1 hour, to finish all those 5 day simulations. So it's efficient, and we are looking at the strategy to further boost the efficiency. So right now the STOF 3D receives the forcing from atmosphere side, there's HER and the GFS, and on the ocean boundary side, we are forced by the GR HAFS, and the On the watershed side, because one thing we did different is we cut the land boundary, not at shoreline, instead 10 meters above sea level, right, in order to account for this kind of coastal transition zones. So that's one of the original purposes, to really account for this kind of coupled inland coastal floodings and including the backwater effects. Okay, so we have a bit of domain that covers the hydrological regimes. So we at the 10-meter land boundary, we receive the inflow from national water model, and the company with national model is extremely simple, right? We just use this one simple one-way force approach. Whenever national water model streams intersect with our land boundary, we just receive that flow and let schism do the rest of the work, right? Route the waters, and also, in addition, you also have direct precipitation onto the entire domain. So we count for that's our attempt to count for the total water level. Next. So in order to do this well, we quickly found out that we really have to do a better job in terms of meshing, right? And the mesh, the river network inside the hydrological regime is extremely complex, and the DEM quality really varies. We struggled with this a lot, but fortunately, we with direct, with working with the data providers, like Colette and USGS and the Blue Topo teams, we are able to really see the translate the improvement in the DEM directly into the mesh, right? So this picture you are seeing is the Mississippi Delta region of the stop 3D. So you can see lots of tiny little streams being resolved, right? So those are full 2D representations, not just 1D features. Next. So last year we published a paper basically documenting the latest development for this type of automatic mesh generators. So it consists of two Python packages. The first step is to delineate the 1D 12x. The second one we expand into 2D, and the output from these two packages will be can be directly used to generate the unstructured grid mesh using SMS, or you can go. Can you click once, please? Click. Yeah, so it's kind of a semi-automatic, but the OS team really took this package even further. So they basically directly use the output from our Python package and use another Python package to triangulate the generate quads and triangles. So they are writing a paper about this. So this whole process can be really, really streamlined and fully mathematic. So this really improves this kind of routing issues, right? So by resolving those very, very small channels. So by the way, schism is an implicit model, so you can go to the meter scale resolution without blowing up the model. Next. So I will quickly show you some results. I'll skip the title part. You can read the paper. I forgot to add the paper. It just appear in the ocean modeling special issues. So what you see here is the long title component. So our experience is that the error for total water level really mostly comes from the really comes from the long title component. The title component is important, but long title component usually dominate the root mean square errors. So this is where the 3D models really shines, right? So you can see this 1 year simulation hindcast we did. The red is observation and the black is the model. So both are both are filtered out with a tides. So you can see this kind of small scale oscillations, interseasonal oscillations and seasonal oscillations. So being captured by the model, and overall for all the co-op stations, the root mean square error is about for the long time component it's about 9 centimeters. Next. So going further, we look at the total water levels. On the left, you can see the bias for all the co-op stations, and on the right is the root mean square errors. So not surprisingly, the bias is usually pretty low. On average, most of the stations have absolute bias within 2.5 centimeters, which is great. We do have some higher bias in some inland stations. We are still investigating. But in terms of root mean square errors, you can see that it's also pretty good. We have larger ones in macro tidal regions like Gulf of Maine, which is not surprising because a little bit of phase shift, can produce the larger errors. But the table on the lower left shows the improvement for just mostly from the automatic meshing methods, right? So from version 4 to version 6, you can see root mean square reduced by about close to 3 centimeters, which is a lot. Thank you. Next. So this slide really harkens back to what I said in the beginning. Is why do we need the 3D models, right? So we did a comparison, for the long tidal pond component between the 3D barotropic model and the 3D baroclinic models. We also added the 2D barotropic model just for clarity. We didn't show here, but the 2 barotropic model results are very close to each other. So what you think here is that really the 3D barotropic model has large biases, and that bias is not constant spatially, temporally. So it's really hard to really tweak the boundary condition to compensate this type of errors. Whereas the 3D baroclinic models, it's natural, right? Because it has some more Halion steric effects. It really captures this kind of variability quite well. Next. So I will say, can you click once? Just click. Yeah. So I'll spend a little bit time talking about our recent work, to use automatic meshing to really try to unite this kind of hydrological regimes with the hydrodynamic regimes, right? So on the right, you can see that from the animation, we are starting to resolve some very, very tiny creeks, from upstream and be able to route the water from upstream boundary all the way to the coastal oceans. We even did a quantitative assessment. The model is doing what it's supposed to do. So this way we can fully account for this combined water effects and compound floodings. So we publish a couple papers now on this for the storm events. But here we are mostly interested in assessing how well model is doing in the hydrological regimes with the latest meshing technology. So it obviously requires high quality DEM. So DEM used to be poor. So there's no way we can resolve any of those channels because channels are not even in a DEM, right? But with the latest meshing technology, we have the hope to really get this under control. Next slide. So this slide shows some preliminary results in the lower Mississippi deltas for USGS stations, right? Some of them have a little bit of tides, most of them do not have tides. So this is a hydrological regime now. And you can see that with the latest this kind of automatic meshing technique, we are starting to get some skills in this regime, right? Including capture some of the small tides, penetrating into this regime and also some of the flooding peaks. So obviously, this regime is highly site-specific, very complex, and some stations just, very complex. They are sheltered behind the structures. For example, I put arrows for the last 2 stations. Those 2 stations are just have lots of challenges. They are really hidden behind the structures. So there's no way we can do this without going into site-specific studies. But with minimum calibration, you can see that the model is starting to get some skills, in this regime. So we have high hope that we can have a reasonable representation for the hydrological regimes in the near future. Next, to summarize, so we have been working actively with NOAA to develop this kind of very efficient 3D coupled hydrologic and hydrodynamic models. And that really opened up a whole slew of exciting new opportunities besides total water prediction. Total water prediction remains our focus for the foreseeable future. But think on the atmospheric side, I can see that this type of work can also improve the hurricane forecast, right, near shore. And of course, it comes with lots of co-benefits. And specifically for Stop 3D Atlantic, we treat it as a test bed, and we improved it over the past 4 years and a lot, by switching from NAVD 88 to GOE-based datum, and we use now the altimetry data to drive the model and the we developed a very efficient automatic meshing tools for those kind of small channels. So right now the model accurately simulate both tidal and non-tidal water levels, and average total water level errors is about 14 centimeters with all the co-op stations. So we are continue to improve that, and the model really shows promise as unified framework for coupled hydrologic and coastal ocean regimes. And in terms of future work, we are actively working with NOAA and the UFS coastal, and we are also looking at some site-specific enhancement for STOP 3D. I'll stop here, and I think I'm run out of time.
All right. All right, thank Joseph. So we just have a couple more, and then we'll leave that for questions after that. So our next speaker should be David Tomilak from NOAA GSL. So I think we talked a lot about storm surge modeling, but a more important factor is also the communication and dissemination of storm surge information via warning services. So GSL works closely with us at the Hurricane Center on the next generation communication or warning systems for storm surge. So I'll let him take it away when you're ready, Dave.
I'm all set. Thanks a lot.
All right.
Everyone can hear me?
Yep.
My name is Dave Tomilak, and I currently work for GSL, Global Storms Laboratory. One of the projects that I'm working on is with storm surge generation. Now, this project's a pretty large collaboration effort, as you can see at the list of names down at the bottom. The storm surge project that I'm going to be presenting is built around a newer framework within the National Weather Service, and it's called Hazard Services. For those that don't know Hazard Services, what is it? Hazard Services is a modernization of a software framework that's used by the National Weather Service to issue watches, warnings, advisories, and other information about hazardous phenomena within the Advanced Weather Interactive Processing System, otherwise known as AWIPS. And so why don't we click the next slide here? So I just want to demonstrate this from a forecaster workflow from an operational perspective, and then I'll just read off the slide here, and then we'll kind of go and break this down into individual pieces. It closely mimics the current forecaster workflow used by the National Hurricane Center and WFO forecasters. Potential storm surge flooding graphics ingested into AWIPS. A recommender from within Hazard Services then run on the input that was ingested. A first guess is generated within Hazard Services. National Hurricane then edits the polygon using some built-in tools. National Hurricane Center then sends the hazard event to the WFOs that are going to be impacted through a send proposed to WFO tool. WFO receives a banner alert, copies that event into a local database with a tool. The event is collaborated on, and then the National Hurricane Center merges the WFO changes with a tool called Merge WFO Edits, and the hazard event is finalized and outputs are disseminated. So let's break this down. Why don't you click to the next slide there? So this is going to be within that Hazard Services Council. Break this down. In this slide, we have that potential storm surge flooding graphic that was ingested. It's a NetCDF into AWIPS. We have Hazard Services loaded. And the storm surge, the forecaster is using this, or getting ready to use the storm surge recommender, which is down in the bottom right. You can see the selection that he has. So let's click to the next slide. So when running the recommender, the tool is going to analyze various metadata associated with the storm surge product, and you can see that storm name, advisory number, hazard type selection, some impacted areas in that. And all these tools the forecaster has control on to make their modification, and then they're going to click on run. So then let's go to the next slide. And then the recommender is going to analyze the storm surge flood graphic and with all the input, and outputs the polygon areas that the recommender tool suggests that need to be acted on. Let's go to the next slide. The forecaster can then use the modify storm surge hazard event tool to make some modification. This tool is specific to storm surge. The goal is to give some autonomy. We want to give the forecasters a tool that'll help them modify geometries in multiple ways. And it can also be used for other components such as evacuation. Next slide. Now this tool kind of shows an example of removing counties with the tool modified storm surge. You can see on the left-hand side, counties was selected on the map. The user kind of chose Shelby, Alabama in the selected geometries, and then the tool goes ahead and makes that modification there. So I want to go to the next slide. And then you can see that the counties are removed. I guess I should have said one more click. All right, next one. Next, the hazard information dialog comes up. Now, once the geography areas have been set, the forecaster will bring up the hazard information dialog. The HIT allows the forecasters to define the metadata of the storm, the start, stop, the category, some of the attributes in that as far as the name, advisory number, bin selections, you can modify those. And then at the bottom, you're going to also see this display geometry differences little box in that. And that's going to allow the forecasters to have some control over viewing added and subtracted areas as data comes in. And so let's take a closer look at that. Let's go to the next slide. So one nice feature of the storm surge is that the forecasters can compare side by side new areas that have been selected. And this particular selection does show you a comparison of the new areas. You can see that down at the bottom left, view added area. So let's click that again. We're going to put both of them on, see what that looks like. So this is displaying geometry differences again, built so that the storm surge forecaster can compare the new data. The slide shows both the subtracted and added data at the same time. Both can be selected at the same time, so you can see both. So let's go to the next slide. So now once all of that data has been finalized, the forecasters will click on preview to bring up what we call the product editor. Now the product editor allows the forecasters to make some last minute changes to the text and review output products before they are disseminated. Now, once the event has been finalized, the product editor appears, allowing the forecaster to disseminate those hazard outputs. Now, some of those outputs include the Common Alerting Protocol, CAP messages, legacy text products, KML for web-based applications, GIS, and there's other outputs that can be added in the future. Let's go to the next slide. And then we'll go one more. So let's just talk about the milestones in that through this project over the last couple of years. So in 2022, GSL developed this distributed cloud environment that would serve as the evaluation platform for this project. Now, the cloud project consisted of the following components. It was broken out, distributed. There's an LDM ingest server that obtained data from the satellite broadcast network, and then we also had some S3 buckets that pull in experimental data models. We had an application server that allowed National Hurricane Center to set up some applications so we could process those. We have a processing server, and then we have a workstation server / instance that renders CAVE, which the forecasters use to display all of the information within AWIPS. Now, this really allowed GSL, National Hurricane Center, developers, forecasters, and other partners to test the storm surge and ingest experimental data in a safe environment for the National Hurricane forecasters to evaluate. Let's go to the next slide. So in 2022 and 2023, the Hurricane Center conducted several in-person evaluations. The goal of these evaluations was to obtain live feedback from the National Hurricane Center, forecaster developers, and other stakeholders during a live event. Let's go to the next slide. So this year was a big milestone because we installed in spring this AWIPS test authorization note. In order to install new software on the AWIPS system and for that the operations folks use, you have to go through a ATM process. And so for us to get that approved was a big deal, and we installed that on the National Hurricane Center's operational AWIPS system. And then in June of this year, we had an in-person evaluation that was conducted. The evaluation provided beneficial feedback to help improve the next iteration of this storm surge project. So we started in the cloud, then we moved onto the operation system for the Hurricane Center. And then why don't we click on the next slide just to see our future efforts. The ATAN evaluation demonstrated refinement in areas of warn relative to the current dissemination methods. Performance improvements are needed within our high-resolution shapefiles, and that was definitely noted this year with our in-person test on the AWIP system. We are currently working on that, and then we're hopeful in 2025 we're going to have an in-person evaluation with improved storm surge software. And I believe that's all I have.
All right. Yeah, so thanks, Dave. Yeah, ultimately, this is really necessary to kind of refine our warning area. The current way we disseminate warnings is a little bit crude and overwarns in many aspects of geography, especially spatially. So hopefully, in the coming years, we can implement software such as this. And I think the ATAN was a great demonstration of us allowing to at least test it out this hurricane season. So, all right, I think we have one more talk. I forget his name. All right, and you're from Google DeepMind. More interested in discussion, so.
Hi everyone, I'm Ferran Alet from Google DeepMind, and I'll be presenting our efforts regarding cyclone forecasting. So basically, first I'm going to talk about our models GraphCast and GenCast, which are deterministic and probabilistic general weather models, and our cyclone results for those. Then I'll present our view on ML for cyclone forecasting, and also future advantages that we see of ML applied to the field. So this is the typical slide we present to ML people. You all know how HFIP looks like. We've trained GraphCast on HFIP, but one thing that might be a bit surprising is that really ML weather research is at the forefront of the size of the output examples that we have to output, because when machine learning typically was working with MNIST, which was very low resolution. Now typical images, when you ask ChatGPT to give you or Gemini to give you one of these images, they're much smaller, as you all know, than a single variable, a single level variable on HFIP. But then we have more than 200 variables and then 40 steps. So it's really like a video prediction at very high with lots and lots of variables. So it's really very challenging from a machine learning point of view as well. So how does our model look like? The GraphCast, which is now 2 years old, but it's still very relevant to us, basically takes these multi-level variables and just makes predictions autoregressively. That means we apply the network multiple times to roll it out every 6 hours. And then its basic components, it goes from the grid to a mesh, kind of inspired by finite element methods. We process the information, we propagate the information in the mesh, and then we decode it back and predict the final weather variables like geopotential, wind speed, specific humidity, and temperature. In GraphCast, we used to have this multi-mesh message passing where there were a few long-range connections and lots of local connections with 40,000 nodes and 300,000 edges. And then the fact that it's a graph neural network with lots of parameter sharing encodes not only locality, but also kind of translation equivariance, nice properties that we'd like our model to have. So the summary is that GraphCast showed better performance on RMSE than HRES from the European Center. You can see here that roughly the advantage was around 10 to 20% depending on the variables. Some variables, like at the very beginning of Tucci, we did slightly worse. Of course, GraphCast had an advantage along in terms of the blurring, but this translated to pretty much almost all variable level pairs. So here you have aggregated in a scorecard where blue is better, deep blue is kind of the best, and red is where we did worse. And you can see that across all the variables, we're pretty much better, except at the very top levels of the atmosphere, where after kind of running the test, we realized we were weighting them very little. Once we weighted them a bit more and made the network care about those as well, we improved the number of variables where we did HRES from 90% to 97%. We then also saw that even though we were training to just predict the weather in general, performance on hurricanes was pretty good as well. So here was Cyclone Lee. After we trained the model, the press contacted us about it because it did very well on predicting it 9 days ahead. But here you can see on the animation that you can see some blurring, even though the track looks roughly right. Of course, it's not just about cherry-picked examples, but more about careful evaluations on long ranges to capture many cyclones. So we did an evaluation over 4 years of data, comparing the performance of HRIS to the ones of GraphCast, and we saw that we were getting roughly a 9-hour advantage, and I think some of you have shown similar results in this meeting. So moving on to our probabilistic forecasts, we have recently presented GenCast, which is our diffusion model, and now it's stochastic, and so it outputs many ensemble members. The way it works is it starts with Gaussian noise on the sphere, and it's basically trained to denoise this noise and try to predict the next time step. It works quite similar to the image generation models that you've seen in the media or that you've probably used yourselves. But it has a few customization for weather. For instance, the spherical, the noise is spherical, and we treat variables very carefully to make good results for weather and not just for instance, good image perception. One interesting thing is that we only train it to predict one time step into the future, and then we continuously apply it multiple times, and that already seems to work very well. We don't need to train it for multiple steps ahead like we did for GraphCast. And we think maybe that's because it already captures kind of realistic weather, and therefore it's kind of more composable. So the runtime for GenCast is about 8 minutes in a TPU, which is kind of the Google version of a GPU. So it's custom hardware, but it's hardware that's widely accessible, and I would say pretty cheap compared to supercluster standards. And similarly to the comparisons with HRIS, we have similar comparisons with ENS, but now instead of using MSC, we use CRPS, this probabilistic score, and you can see again that we get advantages of between 0 and 20%, except at the top levels, because again, we were not training them too much on that. Here you can see some images of Q700, I believe, on GenCast, and you can see that now we are able to output realistic samples at 0.25 degrees of resolution. They're no longer blurred even at 15 days. Of course, the ensemble mean is going to be very blurred, but each specific sample is not blurred. So if we look at the spectral power of GenCast versus GraphCast, you can see that it blurs much less, and it follows quite well the power spectra of ERA5. So yesterday there were some mentions on the track probabilities for Helene and kind of analyzing the kind of its movement along the continent. So I asked some of my colleagues to generate these track probabilities just for context, but they haven't checked them. They just sent it to me a couple hours ago. So here you can see basically the fraction of ensemble members that were within 120 kilometers of the track center. As predicted by GenCast, we have 50 ensemble members, and in purple we have 90%, and it keeps going down. Of course, we can go earlier, and you can see that between 4 days ahead, it starts to get quite well of the structure of where it's going to go. But of course, we can go even earlier, and this is even before cyclogenesis for our tracker, because our tracker is a bit less sensitive than IV tracks. And you can see that it predicts it's going to kind of rise in intensity and eventually go into the main continent pretty well, and it already gives 30% chance or so to hit North Carolina. So for Milton was more predictable. So now we're looking at 5 days ahead. Again, we are maintaining valid time, so we fix valid time and we keep going earlier and earlier predictions. So I think as the NWP models, most of our ensembles were very focused around the right area, 5 days ahead. So we started looking earlier, 7 days ahead. It's still pretty focused, and then we looked at 10 and 12 days ahead. Now, of course, it's much less certain, But you can see that we were still 12 days ahead. I think we were giving around 25% probability of the correct landfall location. So we are pretty optimistic about this. And this again is our GenCast model, but fine-tuned on operational setting. Okay, so one metric that we had in our paper is called REV, relative economic value. I'm sure that many of you will have heard about it. Our inspiration was that in the real life, you all have to make lots of decisions, right? So shall we start discussing even contingency plans? So starting a discussion is relatively cheap. You only have to just chat with your colleagues. Then yesterday I was learning about the decisions and the logistics about sending planes and to obtain measurements and how this is quite costly. And so you better know that the cyclone is coming. But of course, if you want to evacuate a region, this is even more expensive. So you want to be very, very certain about what you're doing before making a decision. So essentially, all this comes to the cost of acting and the loss when you actually don't act and the cyclone eventually happens. So you have this cost matrix of acting, not acting, and then landfall or no landfall, where you incur a cost if you act no matter if the cyclone happens, and then you get penalized if you don't act and the cyclone actually happens. And so whether you act or don't act is based on your expected probability of something happening. And so in particular, there's these decisions that are very cheap, and there's decisions that are actually quite expensive. And so there's this cost-loss ratio where different decisions are going to live in different places, right? So maybe evacuating a region lives on the very right, and starting a discussion is very cheap. It's on the very left. And on the top, you have Oracle performance, so literally knowing where a cyclone is going to go. And on the zero is climatology, and you kind of course, are somewhere in the middle. And you can see that GenCast was significantly better than ENS at 1, 3, and 5 days. So just to put this into perspective, roughly there is kind of different probability thresholds, and they're going to live in kind of different places in the cost-loss ratio spectrum. One thing, so I'm coming to this meeting to kind of learn a lot about how the decisions are made and all of your expertise. And one of these things that we don't know much about is what are these cost-loss ratios that you really care about, how do you make decisions, what the timing of these decisions. So this is one of the things that we would like to learn more. So now some messages that our view of current machine learning for weather, but also specifically for cyclone forecasting. The first one is that ML really moves fast. It's a bit stressful even, and we think progress hasn't even saturated. So GenCast, I was showing you results from, I'd say, last year. We now have results internally that are better than those, and significantly so. And so really, we are moving quite fast. So just to put into perspective, one thing that I found kind of a bit funny and kind of coming full circle. So I used to study, I studied physics and math in my undergrad. So when I moved to machine learning, I was inspired to kind of bring finite element methods back to machine learning. And so as I was alluded before, machine learning usually works with discrete finite resolution. And I was trying to say, hey, problems like weather, they have infinite resolution in the sense that the observations are sparse and actually also not even well distributed on the Earth. So what if we wanted to model a problem like this? And I even found a point in the YouTube talk where I was mentioning kind of this hurricane in Cuba affecting the probability of rain in Miami. So I'm very happy now to be talking in Miami about hurricanes. However, my experiments, so my motivation was nice, but my experiments were very disappointing. I only applied the method of these meshes and so on to the Poisson equation, and it only had 50 nodes. So really, really disappointing in some sense. But we've moved along a lot since then, right? So we now have more than 1,000 times more compute, more than 300 times the memory, and also better engineers that optimize the code a lot. And if we look at future models, we already know that future TPU versions are going to be a scale better than present models. We know that that we can still increase the cost and be much cheaper than NWPs. And we know that there's a lot of value in weather prediction. So we can justify this increased cost as well. Also, I think that there's a lot of scalable weather expertise left on the table. So we know then we need better data efficiency and more scalability because we are roughly already exhausting the data in era 5, and we are also, as a field, moving to observation. So we really need to be scalable and data efficient. So if you look at the spectrum between pure NWP and kind of just a video machine learning where you don't think about the fact that you're predicting weather and anything in specific about the weather, there is kind of trade-offs where you're more data efficient and more interpretable in NWP, but you're going to impose a bias by just the fact that you encode the equations in your way and not a more generic way. And the other part of the spectrum is more scalable. So I would say Gencast and GraphCast were not pure ML, but some part of the weather, but not that much. I think we're going to go slightly to the left while still retaining the flexibility and the scalability of these models. And similarly, I think there's a lot of value into start addressing and incorporating ML into your models. One important thing is that we have an increased emphasis on real-world impact and talking with experts. I think I'm going to skip these pitfalls on GraphCast and Gencast. But basically, one of the big things that multiple of you have highlighted is that we are not showing intensity results. In particular, even the ERA 5 doesn't have enough resolution to capture intensity, but just enough to track the cyclones. So in particular, we are trying to move to dedicated cyclone models, not just predicting the weather and hoping that it works for cyclones. And then we are also trying to understand the capabilities of meta-ensembles between NWP and ML. And then we're moving towards closer collaboration with experts, NHC and Sierra. I know you're here in the room, for instance, and kind of getting a lot of feedback and insights from them to understand the needs and the process of how this works and how we're going to deploy this. And finally, also kind of, I think it's an exciting time to work in this field. In particular, machine learning can bring a lot of benefits and a lot of complementarity capabilities to NWPs. As well as was saying, we have to keep in mind what our real goals are, and ML is very good at targeting specific goals, specific metrics. We also have, it's very cheap, we have many ensemble members, and also it's possible that the mistakes are complementary to the ones that the NWPs make, so meta-ensemble models are going to be very effective there. And if you have more, I'm very happy to hear your thoughts. So that's pretty much it. The message is that machine learning is moving quite fast, in my opinion, and it's showing a lot of promise. And now it's time to kind of treat it as a proper weather problem. Talk more with experts. We're looking towards collaborating with agencies and getting our forecast out into the world. But previously, we need verification and kind of chatting with experts to really understand the problem at hand. Thanks a lot for your attention.
All right, so that concludes this session for the speakers, but we are going to leave it open for questions for the next 15 minutes. So if you guys have any questions for any of the speakers.
I have a question for the last speaker. This is Andy Hazelton from INSEP. Thinking about machine learning. Yeah, sorry. Thinking about machine learning for, obviously, yeah, like you said, like ERA 5 is still not really high resolution enough to get things like intensity. What kind of data set do you think you might need to be able to scratch the intensity problem? I mean, would it be something like a reforecast of a high resolution hurricane model, like a radar data set? I mean, what, how big would it need to be is kind of what I'm wondering, because we have things, but I don't know if they're big enough.
Yeah, to be honest, I kind of came here to know this, to learn this. I mean, we are using IP tracks for verification and validation and things like this. So there is some information already there, and then there is already multiple papers on ML for weather prediction that are using observations, and there's multiple data sets on observations, and I think leveraging those is going to be very helpful. So certainly we have to move beyond ERA 5 if we want to get intensity right. But I was hoping that this community would help us figure this out as well.
Any questions on that?
So a slightly different topic. This might be more for Cody, who maybe, he looks like he's leaving the room. No. I'm just curious with the various hierarchy of storm surge models that were presented, what is the Hurricane Center Storm Surge Unit? When are you thinking about like the time frame for that transition from the traditional shallow water models to something more that has a three-dimensional structure?
Next week? No, I have no idea. So, I mean, we're still trying to figure out the traditional way at the moment. So it could be some time before we get to even that 3D. But it's not like when we talk about total water level, we're not looking at that even in our forecasts. I think one important aspect of this is that guidance is guidance, and the need for us forecasters is still very well there. A lot of what we present, even when we're communicating a storm surge forecast, is slightly guided by guidance, and there's a lot more intuition and forecaster experience that gives you those results that you see. So that's not really answering your question, but just trying to tell you what I want to say to you. So. Here we go.
So again, about Google's DeepMind effort. As I understand, the main energy and the main kind of think about like the main time-consuming part about these ML models is the training part, not the actual result generation part. So I was wondering if you could give us a scale of usually, and usually they say you just train once and you just use it multiple times, but really because you want to improve it, you keep training it. So just can you give us some idea of what that process is? Is it like you have to retrain everything from scratch every time? How much, like in terms of time, how does it look? In terms of energy, how does it compare? Could give us some idea of how it looks.
Yeah, thanks for the question. So right now we are training from scratch very often, but we are starting to do more and more fine tuning, and I think it's valuable for other agencies to also do fine tuning as well. We found it to be very effective, so we're starting to do it more and more. The training usually is significantly more expensive than the eval, except maybe diffusion, because it has these 40 steps. It's still much cheaper, the total compute allocated to inference, than the training, but it's comparable. Whereas something like GraphCast, inference is almost free. Training usually takes 2 weeks on 32 GPUs, and inference can be done in one GPU. Of course, one thing that we could potentially do if after proper verification is kind of having huge ensembles, like 1,000 ensemble members, something like this, but you have to be very careful that properly spread out and things like this. And then finally, to the point on how often we retrain. So far, we started training once a year, but we've also seen that the community in weather does a lot of bias correction and online bias correction as well. So it's something that we're interested in as well. And if people have ideas, I'm very happy to talk more.
Yeah, there's a question in the chat. You see it on the bottom. We'll make that stick.
So I'm guessing the question is on the fact that we need data simulation and the fact that we need the data sets as well. So there has been multiple comments on that as well, and I think we really, like, even when I was showing the spectra of pure NWP and pure machine learning, I moved quite fast, so it may not have been seen, but really even the pure machine learning models were not pure machine learning in the sense that the kind of the past, which is the data set, and the present, which is the data simulation, were NWP based, and we are only providing the future given the present and the past, right? So we really need NWPs to keep improving to get better data sets and better data set simulation.
Yeah, this is Wallace from the Hurricane Center. Another question for Farhan. This kind of ties into the question you just answered, but on that spectrum, you talked about this unexplored area.
Yeah.
And so my question is, what kinds of, like, what do you see in that unexplored area, and what kinds of data or tools that we have now are you going to need? Like, is it more satellite data? Is it a data assimilation system? You know, what kinds of things do you see in that area?
Yeah, I think there's a lot of potential to embed. So there's two types of things. One is observations and thinking about what things have not been assimilated well by current NWP models. So there is, as far as I'm not an expert, but from what I've heard, there is observation that you have that are hard to assimilate into the IC, and then we could potentially add them as extra inputs to the ML models, and that's low-hanging fruit that could be done. The second thing, which I found very exciting, is, for instance, I was talking about this online bias correction. That's something that we could take as inspiration, but there's literally hundreds of ideas on kind of just there on how to do better modeling. And we can incorporate some of these insights directly into the network architecture or the training procedures of our ML models. And for that, we need kind of expertise and chatting with experts to understand what are the key things.
Any other questions?
There's something on the chat.
Oh,
We got that already.
that one.
Yep. Laura, did you have a question? Got it.
Hey, this is Laura Alaka from the National Hurricane Center. Kind of a question or comment for all the coastal impact speakers. I think one of our biggest challenges at the Hurricane Center is having an analysis of the storm surge and inundation impacts. And we saw the high resolution modeling. To Cody's point, guidance is slightly different than that kind of hindcast post-storm analysis mode. How do we get to a point where we have a community accepted inundation analysis, kind of maybe leveraging that high resolution and machine learning information?
Any of the presenters that are online that want to answer that or respond to it? Or Cody, do you have a response?
No, I'm gonna. That's what the Coastal Act was for, yeah. You want to talk about that, or no?
Yeah, it's not necessarily just a NOAA thing, but I mean, this is why the Coastal Act was put in place. The fact that 10 years after Katrina, they're still trying to figure out which insurance company had to pay because it was water or wind, and so the closest thing to an answer to what you were asking is trying to figure out when FEMA finally comes out with that with their model to take the inputs that we create from the physical modeling and then come up with what the damages are. So it's a little bit out of our hands, but having said that, we do recognize that we have to be a broader and broader community. So perhaps it's a good time to start reaching out to them and see whether there can be any more progress made there. But yeah, the Coastal Act is the closest thing that's there. So I have to get back to my roots a little bit. So just out of curiosity, which is the wave model you guys put into Slush?
Oh, for operations, we have a second generation parametric wave model that we use. Oh, it's the Great Lakes wave model.
Okay.
Yeah, but it's not without its deficiencies, but it certainly is efficient. And we have worked a great deal with it over the last few years to kind of improve it as well. So.
And so is the focus mostly on near landfall, or are you trying to go up and down the coast too, in terms of the pure wave driven smaller surges that can be really impactful on just coastal areas still?
I mean, obviously it's coupled to the entire system, so it's basically treated as a subroutine, and you can run it dynamically throughout the whole track. So, but yeah, mostly we're concerned with the near shore wave radiation stresses and what impact that has on the total water level. But not to mention that wave model has been verified, or at least compared against other more sophisticated wave models. So it does a pretty good job,
Pretty good comparison to what you gain with the Great Lakes.
Yeah, I mean, again, we're trying to give out the best forecasts. And I'll be honest, the contributions from waves are not as great as the contribution from surge. At least what we've experienced. So there's a lot of computational costs, even if you incorporate waves. But in the end, storm surge still.
Well, sure, but this is why I asked you where you're looking at, because iPad for Katrina showed that for Katrina that was about 50-50 nearby in terms of the wave-driven part and the non-wave-driven part. And there are well-known areas in the world like San Juan, Puerto Rico, like parts of Long Island, where coastal inundation is almost always wave-driven due to offshore wave conditions. And I completely accept the fact that you want to have a cheap model to go with that, and that the step forward is way more than the things that you are not able to do with that. And so, from a service to the public part, it's an obvious thing to do. But it's kind of cool to take a look at what the best end solution for everything would be. And along that same line, I really liked the presentation about Schism, the fact that it also links in that we're not only doing search for storm surges, but we're doing 3D modeling for navigation, for water quality, and all these kind of things. And the more we have unified tools for these, the easier these are to maintain and to develop.
You said Hurricane Katrina was 50-50?
And wave one, a little bit to the right, that was, yeah.
Total water. I don't know if the total water level was 50% wave.
A little bit to the right on wave one, that area that was more wave.
Okay.
With either the courses online, so.
Yeah. Okay, any other questions? Online? Okay, I think that concludes this session.
Thank you, everybody. Another round of applause for our presenters. And one last call for